Let us take a look at integration, the reverse operation to differentiation. Let's investigate finding the area underneath a curve. So the curve I've drawn here is a part of y equals x cubed. I want to find the area from 0 to 2. Now obviously I don't know the area under that curve. We don't have a formula for it, like we do for a square or a rectangle and so on. So best I can do is estimate it with shapes I know. So I've drawn a couple of rectangles in here. Now clearly my answer is not going to be correct, because we know the area of those two rectangles must be bigger than the area under the curve. 1 times 1 cubed plus 1 times 2 cubed, so I know that it's less than 9. They're what we call the outer rectangles, so the ones that give us a larger estimate. I could also draw two inner rectangles. In fact, the first rectangle is just a line, because it doesn't have any height at all. But that area would give me an area that's smaller than the area that I'm looking for. So I know the area I want is going to be bigger than 1 times 0 cubed plus 1 times 1 cubed. Area is somewhere in between 1 and 9, so if I want to make an estimate, it kind of makes sense to find the average. So I'm going to estimate the area under the curve to be 5. Turns out that it's actually 4. Not a great estimate. So how can I get a better estimate? Well, what I'll do is change the widths of these rectangles. See, if now instead of splitting it into 2 rectangles, I split it into 5, then we can see our overestimate is getting smaller. So it will now be less than or equal to 0.4 times 0.4 cubed, 0.8 cubed, 1.2 cubed, 1.6 cubed, 2 cubed. I now know it's less than 5.76. But if I draw the inner ones in, then we know it's going to be bigger than 2.56. Average of those, 4.16. We're getting closer to the exact amount. Well, what the heck, let's do it again. I'll make 10 rectangles. So here we go, halving the width of all of those rectangles. I now know it's less than 0.2 times 0.2 cubed, 0.4 cubed, 0.6 cubed, and so on and so on. 4.84, but it's going to be bigger than 3.24, the average of which is 4.04. Remember, the exact amount was 4, so we're getting very, very close. So I guess what we'd like to do is make the width of those rectangles as small as we possibly can. Because as we're getting smaller and smaller, that estimate's getting better and better and better. Okay. Well, let's just look at one of those rectangles, and now I've changed it to just some random curve, y equals function x. So let's say that's one of our rectangles. Now, yes, I know the top of that's not a straight line, but remember, if we're trying to make the width as small as possible, then it'll get very close to being a straight line. So I'm going to define this new function, area function. That's what we're trying to find, the area. I want a function for it. So I'm going to define area C to be the area going from 0 to C. Therefore, area x would be the area going from 0 to x. So the area of the rectangle that I'm looking for, well, its height would be whatever the function value is. The width would be x minus c. So the area x minus area c would be approximately x minus c times function x. Okay. But if I rewrite that, function x therefore is approximately this area function that I'm looking for. Area x minus area c over x minus c. But I know the equation of function x. Function x is, well, for the one we looked at, it was x cubed. I could write x in a different way. I could say, instead of saying x, it's going to be c plus h, where h is the width of my rectangle, which is, of course, x minus c. I now get a new little formula here. Area function c plus h minus area function c all over h. H is representing the width of our rectangle. Now, we said we want the width of that rectangle to decrease. And as it gets smaller and smaller, it's going to be more accurate. Well, what that means is as h approaches 0, that area will become exact. It won't be an estimate anymore. So in other words, function x, the function we know, is going to equal the limit as h approaches 0 of a c plus h minus ac all over h. But if h is approaching 0, c will be approaching x. So I'm just going to replace the c with an x. I'm now starting to see something that's quite familiar. That's the derivative of our area function. First principles formula. Limit as h approaches 0 of function, in this case area function, x plus h minus function x all over h. So hang on a sec. What we're saying is the equation of the curve is the derivative of this area function that I'm trying to find. So in other words, if I want to find the area under the curve between 2 points, this is how we write it. It's the long S. The integral symbol, you may or may not realise this, is actually the letter S. It's the long S that you saw, well, you might have seen it in old text. It looks like an F when you see it. But in Old English, it's because it stands for sum, basically. So it's a long S. The function that we're working with, and we're saying, hey, we're doing this with respect to x. The x values are going from A to B. So when we find the primitive function, the function that it came from, I'll go sub that in the B value and I'll sub in the A value. Well, I now know how to find the primitive function. We saw that yesterday. When it's a polynomial, we add 1 to the power over the power. So, okay. If I now have this question, I don't need the diagram. I can say, well, the area under the curve y equals x cubed going between 0 and 2. So the area will be the integral of x cubed dx going from 0 to 2. So x cubed, integrate, find the primitive function, add 1 to the power over the power. Now notice the notation. You're going from 0 to 2. Once you integrate, we go to square brackets. Some people have a straight line. Square brackets, I think, are nicer. And we're going from 0 to 2. Substitute in the 2 minus substitute in the 4. So it was area x minus area c. And we end up with our exact value of 4 units squared. We get the answer that we want. Terminology. X cubed is the integrand. That's the integrand. It's what we're going to go and integrate. So we're talking about nouns and adjectives and verbs here. So x cubed is the integrand. We integrate it to get the primitive function. So the answer is the primitive function. So you integrate the integrand to get the primitive function. Let's try this one. Now, it doesn't necessarily have to be an area. We can still just solve this problem. If I want to find the integral from 2 to 3 of this particular function, okay, add 1 to the power over the power, substitute in the 3 minus substitute in the 2, and I get an answer of 22 on 3. Notice I did not put units on it, because I didn't say this was an area question. I simply said, evaluate this integral. So if I'm finding an area, then okay, I need units. So units squared, of course, for area. But if it's just an integral question, I don't have units. It's just a number, a value I'm coming up with. Negative powers, it still works, even though it's not actually a polynomial, but we still use the idea, add 1 to the power over the power. I've substituted into 1 on x squared because I find that easier, because 5 to the negative 2 might not give me an exact value. It just depends on how good my calculator is, I suppose. So I get 1 on 5 squared minus 1 on 4 squared. I end up with 9 on 800. This is an interesting little question. I want to differentiate the integral of function t to t that's going from c to x. What will the answer be? Well, remember, when we integrate, we're going to the primitive function. So I'll do that first and work out what is it we're differentiating. So I'm going to be differentiating whatever I get when I substitute x into the primitive function minus what I get when I substitute c into the primitive function. Well, if I differentiate this new thing, function x minus function c, well, when we differentiate, you can do things individually. If I differentiate the primitive function, what will I get? I'll get the integrand back again, because you integrate the integrand to get the primitive function. Therefore, if you differentiate the primitive function, you get the integrand. You're going back the other way. So that's nice and easy. If I differentiate primitive function when I substitute a constant in, what will I get? 0. Because you're differentiating a constant. They go to 0. So I'm going to get function x, the integrand, but notice it's x now instead of t because I've substituted x in, minus 0. So in other words, here's a neat little formula. What we're really saying is, when you differentiate the integral, they're inverse operations. They cancel each other out. It's just the pronumeral that's changing. Because at the end of the day, it's a function. It doesn't matter what the pronumeral is. Oh, it could be x, it could be t, it could be z, it could be anything. It's just a pronumeral you're substituting into it. So differentiate our integral, and we just left with that function, the integrand. Okay. 5a, 5b.